Now in this video we're going to look at and review the binomial distribution. You would have seen this in your first statistical methods class and spent some time working with it. We've also looked at it in our review, in particular when we talked about the normal approximation to the binomial distribution. That is the distribution that we were talking about. We're talking about approximating probabilities involving the binomial distribution using a normal distribution. But we're going to be looking in more detail at the binomial distribution itself and using it in some computation in this module. And the reason for that is that the first set of hypotheses that we're going to be looking at involve the use of the binomial distribution. And so let's take a look at this. So we'll first talk about the parameters and the sample space. So we're going to let the random variable x vary according to a binomial distribution based on n trials and success probability p, where n is a positive integer and the success probability p has to be between 0 and 1. So we're going to assume that it's strictly greater than 0 and strictly less than 1. The sample space for this distribution is the set of non-negative integers ranging from 0 to n, so 0, 1, 2, and so forth up to n. If you remember, the way that we think about a binomial random variable is that it's counting the number of successes in n independent Bernoulli trials. So a Bernoulli trial, or a set of Bernoulli trials, is trials that are independent. Each trial has two possible outcomes, which we typically call success and failure. The probability of success on any given trial is the same from one trial to the next. And then, in the context of all that, we define a random variable that is counting the number of successes. And in a first methods class you talk about, and you may even prove or derive the fact that that random variable has what we're calling a binomial distribution. Now, we're not going to prove it, we're not going to derive it, we're just going to use it. All right, and so here I have on this next slide the probability mass function and the cumulative distribution function for the distribution. So the probability mass function, the PMF, of a binomial random variable based on n trials and success probability p is denoted by lowercase f, and it's given by this expression here for all integer values of x between 0 and n. And for any other value that we might plug into it, it's equal to 0. This notation here in the large parentheses, it's not a fraction. This is called choose notation or combination notation. And we read this as n choose x. And then we multiply that against the success probability p raised to the argument here of the function, which we can call the number of successes, and multiply that by 1 minus p. So if p is the success probability, then 1 minus p is the probability of failure on a given trial. And if x is the number of successes out of the n trials, then n minus x is equal to the number of failures. So we have n choose x times the success probability raised to the number of successes times the failure probability raised to the number of failures. And again, this PMF, probability mass function, is given by this expression as long as the argument at which we're evaluating the function, which we're denoting by x here, as long as that is in the range of integers from 0 to n. Now for any other value of x that we might plug in there, so for example 1.5 or negative 3, it evaluates to 0. The cumulative distribution function, or the CDF of the random variable x, is in this notation going to be denoted by cap f. Now the CDF is a probability accumulator. Remember that the CDF of a random variable evaluated at a value, for example, as I've got x here, is defined to be the probability that the random variable capital X takes on a value no more than the argument at which I'm evaluating the CDF. For the case of this distribution, okay, because it's a discrete distribution and because of the sample space, we can evaluate this by summing up the values of the PMF from 0 up to whatever the argument is we're feeding it here. All right, and I'm assuming here that x is an integer from between 0 and n. And then if we plug in this expression for the PMF, then this is what it looks like. So there's no nice, easy, simple formula for the CDF from a binomial distribution, you basically have to evaluate this somewhat complicated expression for each of the values over which you're going to sum things up and then add all that up. So it's a little bit tedious and cumbersome to do, especially if n is large and the x is large as well. But we do want to introduce notation for this because we're going to be utilizing this in the context of this upcoming hypothesis testing situation. Okay, some other useful pieces of information about the binomial distribution. We are typically interested in certain characteristics of distributions, such as the mean, the variance, the standard deviation, the skewness coefficient, and so forth. So the mean of a distribution, another way to describe that would be the expected value of the random variable that has that distribution, is a measure of location. It gives us information about where on the number line that distribution is centered in some way. Now there are various ways that we can talk about the center of a distribution. The standard or the most prevalent measure of location that you looked at in your first statistical methods class was the mean of the distribution. We looked at all of these procedures for testing hypotheses about population means. And in your prerequisite class, you also spent a lot of time looking at how to construct confidence intervals for the mean of a population. In the latter part of your first methods class, you looked at how to compare the means of two populations. And depending upon the course, you may have even advanced to analysis of variance, which is a way to compare the means of more than two populations. So again, the mean of a distribution is just one of several different possible ways of talking about the center of a distribution. The way that we actually interpret the mean of a distribution is that it's the center of mass of the distribution. So again, that's one way to talk about the center of a distribution. It's really the balance point for that distribution. If the points in the sample space were plotted on a number line, and that number line were allowed, if we put a fulcrum underneath that number line, and the number line was allowed to teeter back and forth like a teeter-totter, then the point at which the number line would balance would be the mean. Right? If we put the fulcrum in at the location of the mean of that distribution, that is where that number line would balance. So that is the interpretation of the mean of a distribution. For the binomial distribution, there's actually a very nice formula that we have for calculating the mean of the distribution. We don't have to go back and calculate a summation of a bunch of terms, going back to basic principles, to calculate the mean of a binomial distribution. For a binomial distribution based on n trials and success probability p, the mean of the distribution, or in other words, the expected value of the random variable with that distribution, the formula for the mean of that binomial distribution is just n times p. So it doesn't get much easier than that. This is a really nice formula, all right, that we have available to us. Then the variance is a measure of the variation or dispersion of that distribution. So, how spread out is it? So the mean is giving us an idea of where the distribution is centered on the number line, and the variance is giving us an idea of how spread out or dispersed that distribution is. For the binomial distribution, the formula for the variance is n times p times 1 minus p. So the number of trials times the success probability times the failure probability. So again, this is a really nice handy-dandy formula for us to have at our disposal. All right, it makes doing some of the things that we need to do much, much easier. Now remember that the standard deviation is also a measure of variation. And in some cases, it's preferable to the variance, really only because the standard deviation has the same units as the original data. The variance, you'll remember that the variance is defined to be the average squared deviation of the data around the mean or about the mean. And so because we're squaring those differences, the units on the variance are the square of the units of the original data. So, a lot of times we like to deal with a measure of variation that has units the same as the units of the original data. And the way that we can get that is to take the variance, whose units are the square of the original data, and then take the square root of that. So you'll remember from your first methods class that the standard deviation is the square root of the variance. And when we take that square root, we have to take the square root not only of the number, not only of the value, but of the units as well. So when we take the square root of units that are the square of the units of the original data, we get back to the same units as the original data. So I don't have it shown here on this slide, but the standard deviation of the binomial distribution would just be the square root of n times p times 1 minus p. Now, another characteristic that is important to understand about a probability distribution, and even more so when we're talking about sampling distributions, is the skewness associated with a distribution. So you'll remember that skewness is a measure that quantifies the shape of the distribution. It's telling us whether the distribution is symmetric or if it's skewed one way or the other. And when we say skewed, we're talking about having a long, skinny tail either to the right or to the left. For the binomial distribution, with n trials and success probability p, the skewness coefficient for a fixed value of n. If the success probability p is less than 0.5, less than 1/2, then the binomial distribution will be skewed to the right. If p is equal to 0.5, then the binomial distribution is perfectly symmetric. And if the success probability p is greater than 1/2, greater than 0.5, then the binomial distribution will be skewed to the left. So that is going to be true for any fixed value of n. Continuing on with that thought, for a fixed value of n, a fixed number of trials, how does the magnitude of the skewness depend on p? Well, so for a fixed value of n, the magnitude of the skewness decreases as p gets closer to 0.5. So in other words, the skewness coefficient, whether it's positive or negative, is going to get closer and closer to 0 as p gets closer and closer to 1/2. And as p moves further away from 0.5, so if p gets closer and closer to 0 or closer and closer to 1, then the magnitude of the skewness is going to increase. So that is just some general things that we know that we can state and utilize about the skewness or about the shape of the binomial distribution. If the success probability is 0.5, then we have a perfectly symmetric distribution. But if p is different than 0.5, then the binomial distribution is skewed, and the magnitude of the skewness is going to depend on how far p is from 0.5. Now, we've been talking about for a fixed value of n. Now let's fix p, and let's talk about what happens as the number of trials increases. Now, we know that if p is less than 0.5, then the distribution is skewed to the right. It's got positive skewness. So let's fix that value of p, and let's think about what happens to the skewness coefficient for that distribution as the number of trials increases. Well, as the number of trials gets bigger and bigger and bigger, the skewness, that right skewness, is going to decrease, decrease, and decrease, get closer and closer to 0. And visually what that would look like is that the distribution is getting less and less skewed. It's getting closer and closer to being symmetric. On the other hand, if p is greater than 0.5, we know that the distribution is skewed to the left, but as the number of trials increases, again, that skewness is going to be attenuated. It's going to get closer and closer to 0. It's going to look less and less skewed. It's going to look more and more symmetric. And then finally, if p is equal to 0.5, well, for any value of n, if p is 0.5, the distribution is symmetric. So the skewness coefficient is not going to change in that case. It's always going to be 0, but the graph of that binomial distribution would actually look more and more like a normal distribution. In fact, all of that would be the case for all of these situations. Regardless of what p is, as the number of trials increases, that binomial distribution is going to look more and more like a normal distribution. In fact, that is the basis for the normal approximation to the binomial distribution. So these are some basic but very important characteristics of the binomial distribution. And again, it's going to be very important for us to be comfortable with this distribution and to know how to work with it and manipulate the functions, calculate the various values. Let me scroll back here real quick. We're going to need to know how to calculate these things in an efficient way And in the examples that I'll be working where I'm dealing with the binomial distribution, what you're going to see is that I'm going to be using the TI-84 to do these calculations. You could also use the TI-36X Pro, and there are various other calculators that have these distributions built in. If your calculator is designed to be used in a statistical class, then more than likely it's going to have these distributions built in. So, like I said, I've got my TI-84, I've got my TI-36X Pro. Okay, both those calculators have the binomial PMF and the binomial CDF built in. So in other words, looking at this PMF right here, if I want to calculate the probability that a binomial random variable is equal to a particular value, then using these calculators that I'm talking about, it will calculate this whole thing. I won't have to do it piecewise. I won't have to calculate n choose x and then multiply that by p raised to the x times 1 minus p to the n minus x. I won't have to do all that. I'll just have to plug in, I'll have to tell it what n is, what p is, and then plug in the value for x, and it will calculate this whole thing for me. Now that's nice, but what's even nicer is that these two calculators have built in the CDF of the binomial distribution as well. And so to calculate the value of the CDF at a particular value of x for a particular binomial distribution, all you have to do is tell the calculator what n is, what the number of trials is, what p is, all right, what the success probability is, and then plug in the value at which you want to evaluate that CDF. And it will do that automatically within the calculator. You won't have to calculate each of these individual terms and then do the summation yourself. So that's going to be a great savings in terms of time and effort, and also you're going to increase your accuracy by many orders of magnitude, because if you have to do this much by hand, probably anybody's going to have lots and lots of errors. So these are great calculators for doing this kind of work, and so I would highly recommend, number one, learn your calculator. Right, you have to know how to use it, but also check to make sure to see if it has this kind of functionality, because if it does, use it. You know, I'm not putting any restrictions on you in terms of calculator usage. You can use whatever calculator you want, and you can use its full functionality. That I would hope that you would do that. So it's going to be very important, again, that you're comfortable with the binomial distribution and you're fluent in performing these calculations, and preferably having a calculator that will do these calculations. Now, I've mentioned the TI calculators that I have. There are also Casio calculators out that are fairly inexpensive that have these distributions built in as well. So if your calculator currently does not have this functionality, look around at the calculators that are out there now. I know you'll be able to find one that can do these calculations. Okay, so to finish up this particular lecture, I really recommend that you get some practice in the next several days using the binomial distribution, just to kind of bring yourself back up to speed. And to facilitate this, I have posted a practice problem worksheet on the binomial distribution on Moodle. And so I recommend that you download that worksheet. By the way, it's a worksheet that I've used for several years in my 7003 class, my Statistical Inference 1 class. And because it is considered review material, I'm just bringing that into this class as well. So anyway, download that worksheet, work through those examples. I will post the answers to that worksheet in a day or two. And the solutions for this particular worksheet, I do show you how to do some of these things on the TI-84. So if you have an 84, you'll be able to see how to do these. But regardless, you will have the answers. Now, some of you may be very comfortable with the binomial distribution. Others of you may not be quite as comfortable. So you are free to work as many of these problems or as few of these as you want and feel are necessary for you to get up to speed, and to get more comfortable with this distribution. If you work all the problems on the worksheet and you're still not quite comfortable, just let me know, send me an email, and I will create some more problems and other worksheets for you to work. Be happy to do that. Okay, so I'm going to stop the video now, and we're going to be moving into this new technique for testing hypotheses. And so I will see you in the next video.